In this video, we're going to look through a number of examples of zero force members in trusses. I'm going to start by just reviewing the fact that zero force members is on your Hibbler crib sheet for the final exam or for your exams, at least for Missouri S&T students. And so this first rule here is what I call the elbow rule. And basically, if you look at this joint D right here, there's no external load here. You just have two members. And so if you basically sum forces at D perpendicular to this member with no other force, this guy has to be zero. And then once you determine that he is zero, then of course this guy is zero. And then you can remove these two guys. The same is true down here at A. There's two members, AF and AB, coming together at A, but there's no external load there. So if you draw this member, this joint at A, and you've got a force in AB and you have a force in AE, and there's no other external force. If you sum forces vertically, this guy has to be zero. If you sum forces this way, this guy has to be zero. That's the elbow rule. The T rule is depicted here. And remember, the T rule is where you have three members coming together. Two of them are collinear, and the third one comes off at some angle, and there's no other force acting there. For example, here at D. And so if this is like some x prime, and this is some y prime, once you've drawn this joint at E, then you can sum forces in the x prime direction, and this guy has to be zero. If you come down here to C, this is also the T rule. And so if you draw a picture at C, it looks like this. There's no external load. These two are collinear. And so if you sum forces in the x prime direction, this guy has to be zero if there's no other force acting there. And again, you say, no, wait a minute, these members go to A, and so A is this complex joint. And you're going, yep, it is a complex joint. However, remember, we said that most members on trusses have a simple end and a complex end. And so if you analyze the simple end of a member, then you have analyzed that member. A member in a truss has a single internal load, either tension, compression, or zero. Once you find that internal load from one end of that member, then that is the internal load in that member. And don't worry about that this other end looks complex. It's just indeterminate. So again, the principle applies that for a truss, that if the whole truss is in equilibrium, then every piece of it has to be in equilibrium. So the two rules are on the Hibbler crib sheet. We're going to start going through some examples. We'll finish this video, and then we'll do some more examples in another video. So here's an example here. This is a truss that's cantilevered. It's sticking out from a wall. And DC and BC are just hanging out here in space. So if you draw a free body diagram of joint C right here, you've got a member DC and a member, and I didn't draw these as arrows, so I didn't draw them pushing or pulling, because I don't need to know that right now. At C, and there's no external force here. If I sum forces vertically, this guy has to be zero. And once you identify him as zero, then of course this guy has to be zero. So those two are two force. If you look at joint A, strictly speaking, this doesn't follow the elbow rule or the T rule, but this follows the RACAR rule, the right angle corner at a roller. So this is a right angle corner at a roller. So there's just a horizontal support reaction here. And if you draw that picture over here of joint A, FAE is vertical, FAB is horizontal. And if you sum forces vertically, FAE has to be 0. If you sum forces horizontally, FAB has to equal, if this is EX, has to equal EX. And so this guy's 0 force right here. If we come down to this example, we got an elbow, actually all of these are elbow rule examples. Up here, D, you've got, again, 2 members, there's no external load. So if you look at D, basically this guy's 0 and this guy's 0. How about here at F? If you look at F, this is actually another example of the RACAR rule, because this is right angles. This is not a roller, but it's a load that's collinear with one of these members. And so this guy, if you sum forces, if you look at analyze F, if you sum forces vertically at F, so that looks like this. So this is F, FE, F, F, E. This is the P load, and this is F, AF. If you sum forces vertically, this guy has to be 0, this guy. If you sum forces horizontally, FE has to be P, and that's equal to P, and he is compression, because he's pushing. P is pushing on this joint, and so he's going to be pushing on the joint. And so he's pushing on the joint, which means the joint is pushing on him, and so he's in compression. There's no other 0 force members on this guy. If we come down here to this example, this is actually the same one of the crib sheet that we just looked at. But this is the elbow rule. So this guy is 0, this guy is 0. This is the elbow rule. This guy is 0, and this guy is 0. Here's another example. And these examples just came from a Google search, actually. And so HG and HA are hanging out here in space. There's no loads up here. If you analyze joint H, you basically have F, H, G, and F, A, H. There's no external loads here. So you basically sum forces, and they're at right angles with one another. You sum forces vertical, this guy has to be 0. Sum forces this direction, this guy has to be 0. Do you see any other elbow rule on this guy, or T rule? So actually down here at D, it's the same situation with no external load, just 2 members. This guy has to be 0, and this guy has to be 0. Five, do you see any rules that apply here at 5? So there's actually a couple rules that apply. So out here at A, you've got 2 members coming together. There's no external load. If you analyze A, it basically looks like this. And there's no external load. So if you sum forces vertically, this guy has to be 0. And then once you find him 0, then this guy is 0. So this is 0, and this is 0. But once you identify both of them 0, what about BE and ED? So they're basically BE and ED are hanging out there just like this. And this is E. There's no load there, external load there. Now there's some complexity up here, but this is the simple end of BE. And if you sum forces vertically, this guy has to be 0. And sum forces horizontal, this guy has to be 0. So this guy simplifies to just a triangle with the 4 kilonewton force up there. Just the way it's loaded, anyway. Now, if you hung a load here, it would change. If you hung a load here, it would change. But on the current loading, it basically simplifies to just that triangle. Finally, if you look at this example 6, if you look for zero force, so D is the elbow rule. So out here at D, you basically have these two members. There's no external load, nothing else going on. If you sum forces vertically, this guy has to be 0. Once you find him 0, then you can sum forces horizontally, and then this guy is 0. Once you find this guy 0 and this guy 0, you can take them away. Well, then you basically have FE and EC out here. And so you got FE and EC at joint E. There's two members, no external load. Basically, some forces vertically, this guy's 0. Some forces horizontally, this guy's 0. And so all of these members go away. So you're basically left with I just shouldn't have drawn those. You're basically left with this much here and this triangle coming down. So that's 0 and that's 0. So again, you're learning to look at these and find those zero forces. You're greatly simplifying your analysis. We'll stop this video at this point and then we'll start another video.